Okay, so thank you everybody for the amazing talks, and also thank you for having me. My name is Nicolas Müller. I'm a research scientist.
Mr.
at
Müller, if I
Fraunhofer
may
AISEC.
interrupt, you have on the top right, you still have another window that is.
Oh yeah, thank you. I think that's speakers. Better now?
Better.
All right. So my name is Nicolas Müller. I work at Fraunhofer AISEC in the domain of audio deepfakes, both in the creation and detection. And today I want to show you what my research group is doing in this domain. Here we are. So there's basically two main activities that we're doing. On the one hand side, we are cloning target persons. So we are effectively creating audio deepfakes. And then on the other hand, we are also working in detecting audio deepfakes. So the main question is, why are we even creating audio deepfakes? And the reason is because we A, want to understand the technology, we B, want to build demonstrators, and C, we need the data to train the detection algorithms. So I want to show you what we have currently in the domain of audio deepfakes. So there is this YouTube demonstrator we have. It's a GUI, it's a web front end where you can clone the voice of Angela Merkel. So you can just type in whatever you want, and then she speaks it. And I just want to try and share the video with you. I'm not sure if it works, but we can try. So let me see if I have to. Okay, I just started, and please somebody tell me if you can hear it or not. Did you get that?
I didn't hear anything.
I couldn't hear as well.
Okay.
There's no voice.
Yeah, okay. Then I'll just paste it into the chat. And or maybe Mr. Wolf, you can paste it into the chat. So anyways, what you can see if you look at the video is that you can enter a text, and then it is spoken by the German canceller. And I just want to give you a brief introduction how this works, and then I want to show you how we use this technology to detect deepfakes in the audio domain. So you train these systems by collecting a training data set, which consists of pairs, audio, and text. So basically, you crawl YouTube for speeches of Angela Merkel, and then you have a bunch of fragments. You put them into a data cleaning and pre-processing pipeline. So you split the longer speeches into shorter segments, and you do a whole bunch of technical stuff. So, for example, I have brought you here one pre-processing step, which is taking the raw audio waveform, which you can see in the upper half of the image, and then transforming it to MFCC, which is a spectrogram and which is easier to work with for the computer. And yeah, then basically you start the model training and evaluation. And so model training, these are pretty complicated models. I won't go into them in detail. But what's interesting about them is that they have some resemblance to how humans would work. So they take in the input text that you provide, and then they have an attention mechanism, which basically looks at the characters that you want to be spoken, and then like synthesizes them. So you put in a text, and then out comes the waveform. And what are some challenges in this field? So the biggest challenge is the training data, not necessarily the amount of training data. We have enough public speeches of the German Chancellor, but the quality of the training data. So the mapping of a phoneme to the actual sound is a one-to-many problem, right? Because you can speak a single character, for example, the A, in a variety of different ways. So this is this is something that makes it hard for the model. So if you don't want your voice to be cloned, then what you can do is you can try to speak in like a non-monotonous way, or introduce like background sounds into the voice, or maybe the occasional clapping or some artifacts from the Skype transmission. And these make it very hard for the system to synthesize a new target. We can also see this if we try to clone the Markus Söder. He talks with much more style and expression than Angela Merkel, and our system has much more problem cloning him. All right, so what can we do to detect audio deepfakes? Well, we can also use the feature-driven approach. So we collect a data set which consists of audio files and then a label, where the label is true or false, corresponding to either the audio being fake or authentic. And then basically what you have is like you have a huge list of audios which are either true or fake. Then you apply a whole bunch of pre-processing steps, like I showed you earlier, and then you can train just a classification model. So what we did now, we trained such a model, and we also like started a little online experiment where we played audios to users, and then they had to say whether the audio was fake or real. And they competed in this deepfake detection against the AI we trained. So it looks like this. We'll post a link to the video in the description as well. And so you see the interface here, and it's like the game consists of rounds. So you can press the start button, and then the audio plays, and then you have to say if the audio is fake or benign. And the AI deepfake detection does the same, and then you like can compare scores. And that's what I want to show to you today. So we had 200 users, so a rather small group, who played around 9,000 rounds. And then here we see the accuracy. On the x-axis, you can see the different attack IDs. So there were what is it, 13 different attacks. So attack is a deepfake creation system. So there were 13 different methods of creating deepfakes. And this here are the benign data. And you can see that the users, they never achieve, like averaged over all the users, like any attack is able to fool at least some users. So let's take, for example, the A19 attack. It fools about like 90%. The users have an accuracy of 90%. So 10% of the samples played to the users were classified incorrectly. And what we can see here is, we can see that users generally can be fooled by a variety of deepfake algorithms. So it's not just one algorithm that fools the user, but there are many. And we can also see that there's a quality difference in the attacks. So for example, this A10 attack, which was WaveNet, is much harder for the humans to detect than, say, the A13 attack. So let's compare that to what the AI obtains. So these are the scores for the deepfake classification algorithms. And we see that it has a much higher accuracy on average, but interestingly, the A17 attack could not be detected very well by the AI. So we can just plot the difference, right? So a bar of which points upwards indicates that the AI outperformed the human by this amount. So on the benign data, the AI outperformed the human by 0.2. And we can see that the AI consistently outperforms the human, except for one attack, which is the A17 attack. So we are planning to extend this experiment using more data, using more users, but the preliminary results indicate that while deepfake detection has a clear advantage over humans, there are still some attacks which are very hard for the algorithm to detect. One last thing which might be interesting, so we asked users to classify their IT skill from lowest 1 to highest 5, because we wanted to know if users who are familiar with IT can detect deepfakes better than users not familiar. And what we saw is that for most cases, it doesn't make a difference. So even if you're an expert in the domain of IT or computer vision or machine learning, like statistically speaking, you don't have a higher average in detecting deepfakes. All right, I think I don't have to go into the use cases. Yeah, there's already some attacks that have been done. Some companies have been tricked into sending money. Yeah, so that's all from my side, and I'm happy to answer questions.